Georgia State University, and I'm going to tell you a little bit about a project that we're working on right now, trying to hunt for AGN outflows. So quickly, what are AGN? AGN stands for active galactic nucleus. And so what an active galactic nucleus is specifically a supermassive black hole in the center of some far-off galaxy that is accreting a bunch of matter onto the black hole. And so paradoxically, this ends up making a bunch of radiation come streaming out from near the black hole. So the black hole itself is not emitting any of this radiation, but a bunch of the material that's spinning inward from near the black hole is heating up, and so then that stuff is what's actually emitting a bunch of radiation. So we have this supermassive black hole in the center here, and it's surrounded by this torus of gas and dust, and then inside of that is a little accretion disk where all the matter is spinning around into the black hole, and then this torus actually funnels all the radiation that's coming off of this accretion disk into this biconical shape that's perpendicular to the torus. Okay? So typically when we're looking at galaxies, they are hundreds of thousands of light years in diameter, and so they're very easy to see. We see them all the time. Unfortunately for us to observe AGN, it's really impossible because the size of these things are several light days in size. So if you were out looking at the posters earlier, Dr. Dunn was talking about how he studies AGN, and the torus is typically about the size of a little bit bigger than our solar system. So the accretion disk inside is definitely the size of our solar system, and then maybe this is out to like the Oort cloud. So very, very small and very, very far away. We're never going to see them with the current technology. So what can we do to kind of get an idea of what these things look like if we can't directly see them? What we can see is the narrow line region that is outflowing from these AGN. So as I showed in that previous picture, you had the torus, and perpendicular to the torus, you had that flood of ionizing radiation that's perpendicular to it. And so these structures are actually hundreds to thousands of light years wide or long. And so they are easily resolvable if we look at them in the right wavelength. So this is a picture of a galaxy NGC 1068, and it has an AGN in the center. And so what we're seeing here, there's three colors. The red is X-ray emission, the bluish purplish is radio emission, and then the green is this optical light. And so the brightest optical we can see here also matches with the radio is this conical feature right here. So this is one half of the narrow line region that we can see. The other side is below the host disk, and it's obstructed from our line of sight. We can't see it in the optical. So if we look at it in the infrared, that'd be possible. So this large structure, which is directly related to the AGN in the center of this galaxy, if we can figure out the orientation of this narrow line region, we can thus say that we kind of know the orientation of the AGN inside. And so knowing the orientation of the AGN, something we can't see, is really important to a lot of theorists and a lot of other observational astronomers who do a lot of calculations which include an inclination of the AGN to our line of sight. So if we know the inclination of the narrow line region, we can thus know the inclination to the AGN. So how do we do that? Oh, I guess, yeah, so as I just said, the inclination to these AGN is unknown. And so if we know the inclination of the narrow line region, we can figure out what the inclination is of this perpendicular torus, which is really neat. So the way we do that then is we actually measure the velocities of the outflows in this narrow line region. So step back a couple steps. What we're actually seeing here is this outflow of gas and radiation that's pushing out all this gas. And so we can kind of see, or we can measure how that is oriented with respect to our line of sight. So this is a picture. It's flat. It's two-dimensional. It's a projection. You have no idea how this is pointed toward us out of the image. So we have to use some sort of information besides imaging to figure out what the orientation is of the narrow line region with respect to our line of sight. So what we actually do then is we look at the velocities of the outflows, and we measure the velocities to try to figure out how the narrow line region is pointed at us. So if we look at one cone and it's all of these velocities are red shifted, or they're traveling away from us, and then the other cone has a bunch of velocities that are blue shifted or traveling toward us, we can figure out that the orientation of the narrow line region is fits to some specific model. So we need to measure the velocities of these outflows to figure out what the orientation is. So basically we can do that with spectroscopy. So basically what we do is we use emission line spectroscopy. That's where you have a cloud of gas that is heated up and it's emitting photons. And then if that light hits a prism, we can see specific bands of light that correspond to just certain wavelengths of light. So we're looking at this emission from the gas in the narrowline region, specifically the Doppler shifted emission. So what we want to see to figure out what the velocity is of that gas traveling toward or away from us is we measure the Doppler shift of the emission line gas. So I don't want to talk to you guys online. I just want to talk to you today. And so, so what we do is we measure the Doppler shift by just looking at the shift in the wavelength of light as it's traveling toward or away from us. So everyone should be familiar with the Doppler shift. You have a race car traveling toward you, it has a higher pitch sound, and as it goes by you, the sound gets more boom. So the same thing can happen with the emission of light. So here is a very stupid person looking at a sun, and so you can see if the sun is traveling away from us, the wavelengths that it emits are actually stretched out and appear redder than if the star or the sun is traveling toward our eyes, and then the wavelengths get scrunched up and it actually has a shorter wavelength. So here is the spectrum of a star or the sun at a rest frame, not moving, and then if it's traveling away from us, the absorption lines in the spectrum travel to a redder wavelength, and if it's traveling toward us, the absorption lines are traveling, they become bluer and are visible at a bluer wavelength. So this is the same thing that can happen with emission lines. It's just a different type of situation with cold gas versus hot gas. So we look at emission lines instead of absorption lines. But if we just measure the change in wavelength versus what it should be at rest, we can figure out what the velocity is of that gas. And so we just determine what the velocity of these outflows are by seeing how the emission lines are shifted from what they should be. So what we look at then is specifically, this is 1/3 of that previous narrowline region image. This is just the optical light. And so what we're looking at here, this is a spectrum. So if you went back and looked at a spectrum in a 2D format, it would look something like this. If we just cut out a slice and stood it up, it's going to look something like this, where you have these emission lines that are very bright at specific wavelengths. And so what we look at here are these narrow emission lines, which are your oxygen emission lines, and they're narrow. And so we look at those because they're a signature of the narrowline region. So that's why we call it the narrowline region, is because we're actually just seeing this highly ionized gas in the form of these narrow emission lines that we can track to figure out what the velocities are. So looking at this optical emission line and whether it shifts back and forth, we can figure out the outflow velocities of this narrowline region cone thing. So then just putting the Doppler shift back into what we're doing, we're looking at the gas as it's traveling either away from us or toward us, and that gas then shifts the photons that are streaming into our eyes, and they appear either redder or bluer. And so for, that way we can detect what way the narrowline region and thus the AGN in the center is pointed. So I use the Hubble Space Telescope to do this, and I use an instrument on it called the Space Telescope Imaging Spectrograph. And what that is a long slit spectrograph where you take a slit of across an image. So this is another narrowline region. It's not as sexy as the previous one for 1068. This is Markarian 34, another narrowline region. And so this is the nucleus, and you can see this time there are two cones in the plane of the sky. And so the way we measure the spectra then is along these slits, we take a bunch of spectra, and then it's laid out in a two-dimensional format. So that's what this is, where along the slit, you're getting spectra every maybe 0.05 arc seconds. So each one of these rows is another spectrum of that gas emission. And so these are those two bright lines that I highlighted earlier, and we can see as you go across the narrowline region, the wavelengths are bluer at some points and are redder at other points. So this is where we're starting to detect the Doppler shift of this emission to figure out the orientation. So then we can begin modeling the velocities to figure out what the geometry of the narrowline region is. And we need two things. We need both imaging, because we want to make sure that the model that we create agrees with the image that is seen in the sky. And then we also need the spectroscopy, the velocities. So this is just like that picture that we just looked at, kind of turned on its side. So this is wavelength or velocity, and this is position along slit. And this is now wavelength or velocity, and this is the position along the slit. So we can see that it has these high velocity components that we are crediting to the outflow from this bicon. So we can look at the velocities, and we can look at the geometric structure to come up with a three-dimensional model. It looks like this. So here we have a 3D model that has velocities that are traveling outward from the nucleus, and you can see as they travel outward, they accelerate and begin to decelerate. Why? Because that's just what our data shows, so we have our model that just simulates that. And so what this 3D model then creates is a velocity diagram that we sample with a position that is exactly like the long slit position from our Hubble observations. So if we look at, this is the narrowline region, the geometry that we create, it looks like that one I just showed you, and then we sample along this exact same position to sample what the velocities are along that model, and we can compare them to what the velocities are that we observe. And so from that, we get what's called the chi-by-eye fit, so the best fit of these shades to these velocities as possible by our eye. And from there, we can determine what the geometry is of the narrowline region. So that's really great. So the hunt begins in that since we have this nice model laid out, we're going to try to look at all the AGN that we can and figure out all the inclinations that we can, and hopefully that'll tell us something about the way that we observe AGN. So we went and gathered all the spectra that we could from the Hubble Space Telescope, and we got 52 different targets. So 5 of them were previously published by our group, so we didn't really look at them again. But then the rest was archival data, so we went into the archives and other people observed these AGN. They said, great, here's some science we did with it, and then they left the data there for us to use, which is great. And then another 11 AGN were targets that we proposed for privately to use the data for our own uses. So 52 different AGN. So we used our model and determined the inclinations for all of them. Not really. Actually, it only turns out that a third of the AGN that we observe actually have outflows. For the rest of them, there are no signatures of outflows, which is very bizarre. It's nothing we expected at all. So the 1/3 of them, though, do have these outflow signatures, these high velocity 4 components of outflow, multiple components of outflow, that we're able to fit a model to. So a third's not bad. We can still start looking at things versus inclination with 17 targets and see what we can come up with. So here is the comparison of the inclinations that we get. That's the x-axis here. And we compare them to an infrared color. So the infrared color is taken from Spitzer Space Telescope observations. Their infrared telescope, where you're just looking at the flux at 2 different wave bands. It's 5 micron and 30 micron. And so if we just look, use Wien's law, where if you think of a black body and the peak wavelength of that black body is going to be equal to or multiplied by some temperature to give you this constant. So if we look at 600 Kelvin dust, that's going to be really prominent at 5 microns. And then the much cooler dust is going to be more prominent at 30 microns. So if we just look at the comparison of hot dust to cold dust, we see that the inclination, there's a trend with the inclination and the ratio of those colors. So what this is saying is that if we look at it in a more, this torus at a more face-on position, we're more likely to see the hot inner throat of the AGN, and you're seeing this hot dust, this 5 micron dust, much more prominently than if we're looking at it from an edge-on position, where we're only seeing the outer cool 30 micron dust. So this is just showing that these inclinations that we're deriving from our models is actually showing some trends with a physical observable parameter. This is really neat because if we are able to hone this down to be a little bit more specific, we can look at thousands of AGN and look at their colors and then determine what the inclinations of all those AGN are without having to do our very intricate narrowline region modeling. So to have some sort of cheat key to look at all these targets that are at much higher redshifts would be very useful to the astronomical community. So that was a really neat byproduct that we were able to pull out of this. So then the question is, if we only are able to observe a third of them, what about the rest of the sample? So the rest of the sample, I deemed like some of them to be ambiguous because these kinematics, if you guys ever looked at the kinematics of like the rotation in our host galaxy, you have this similar pattern, and so here's that target, and we can see the narrow-line region. It has this conical structure, but these also appear to be some sort of dust lanes. So maybe what we're seeing is some sort of rotation in the host disk, and the gas in the host disk is being lit up by that narrow-line region. But we can't really fit an outflow model to that. So that needs to be further investigated. And then additionally, there are these what we call complex targets, and they're just really screwy. As you go all the way across the slit, they just have these kinematics that just go across systemic velocity, and can't really make any sense of that whatsoever. So those are really bizarre. And then there's a bunch of other ones that are just really too compact. So this is the spectrum again. As you go across the nucleus, you get a little bit of emission, but there's nothing above or below the nucleus. So we can't really come up with any model whatsoever. And those are just compact and boring. Oh my gosh. So, yes. So 2/3 of the sample then are unable to be modeled, which is not horrible. I mean, it was a downer at first, but it also makes it much more interesting to figure out what's going on with the rest of these. Are there actually not any outflows? Are these biconical regions of narrow-line regions? Do they not exist in these targets, or are we just not being able to see them? So what we're proposing is that most of them, we're just not getting enough information. So HST observations, you get this one slit of information. So here is another one of those fancy images of the optical emission. And we can see that from the stiff slit that we currently have for Markarian 509, we're already missing this really cool feature here that looks like to be some sort of check mark, some sort of filament, where you're having something fall in maybe and it hits the disk and it falls into the nucleus. We're missing all of that. So it's really difficult to get that with a single slit. So we could go, dear NASA, please give us a bunch more observations. And they would say no, because that is expensive and it's silly and you're not going to get that much more information that's really relevant to you. You probably get just this much, and that's only another arc second. You're still missing a bunch more of this filament, and you don't know what's going on here or here. Maybe that's where the sexy stuff is, and you're missing it. So no, you will not get that time. And so we say fine. And so what we then do is we go to Gemini or any other telescope that has what we're going to call an IFU, which I'll talk about in a minute. I'll say, oh, Gemini or other telescopes that have an IFU, can we observe with you guys? And they'll say yes, and they're very nice about it. And what they do is they give you, instead of a long slit, they'll give you a large field of view where you can look at these spectra in all of these all at once. And it's very fun. So an IFU is an integral field unit. And so it's different from a long slit spectrum in that the long slit is only getting spectra along the slit. And so an IFU, you're actually getting a spectrum at each individual pixel of the picture. So here's a cartoon of what an IFU, or an integral field spectrograph, looks like. And so with IFU, you're able to actually combine spectroscopy and imaging in one single observation. And so that saves you a lot of time, because previously we needed to both get the long slit observation and the image. These are two separate observations that you'd have to propose for. So this is actually just one observation where you're getting a picture, but then at each individual pixel you're also getting a spectrum. So that gives us the squared amount of the previous data that we were able to previously obtain with STIS, which is much nicer. So if we go back then and we look at Markarian 509, now we aren't observing it with STIS anymore, that long slit. Now we're using this field of view. And so if we zoom in, this is what it looks like with the actual instrument observation. And so we can see that filament coming in again, which is nice, and then the nucleus here. So if we look at each individual pixel and we try to measure the velocities with respect to our line of sight now, we can see two interesting things that are happening. One, most of the kinematics are actually rotation. So you have blue shifted over here, red shifted over here. This is a disk that's traveling in a counterclockwise manner, so that this disk is traveling away from us, and it's red shifted. This disk is traveling toward us, and so it's blue shifted. And so if we ignore that stuff, we still don't see outflows. What we actually see is this filament that we were looking at before. And it starts off as a really high blue shifted velocity. It's coming at us really quickly. And then as it comes closer to the nucleus, it stops and starts falling into the nucleus. So this is not, even though it's blue shifted, so that means that it's traveling at velocities toward us from the galaxy, what we think is actually happening is that there's some sort of filament, and you can see it reach all the way back up here, that it's coming from behind the galaxy in the plane of the sky, gets stretched out, runs into the host disk, and then begins to decelerate and then fall into the nucleus. So what we believe is actually happening here is not outflows at all, but inflows. We're having some sort of minor dwarf galaxy being ripped apart, and then the remnants are being fed into the AGN in the center of this galaxy. Really neat. This is the first time that it's ever been seen directly happening. We're catching an AGN in the wild. We were hunting successfully, and we caught an AGN eating a young dwarf galaxy. Poor bugger. So yeah, that's really neat. So this is our toy model then of what we think is happening. Just to back over the head a little bit more, we have this disk that's rotating, and on top of that, we also have this filament that's coming in, decelerating, falling into the AGN. Oh, it's really cool. The interesting thing maybe, though, is that we actually are seeing no evidence of biconical outflows. There's no narrow line region bicone in any of our observations for this. So that's actually the really interesting part. So what we need to do now is to go back to the rest of that 2/3 of that AGN sample and figure out what's going on with those and see if they have outflows or not, or if we actually did just miss them with the STIS long slit, or if they don't actually exist, such like this AGN Markarian 509. So in summary, an AGN is this supermassive black hole that accretes matter, and in the process is also emitting a ton of radiation from the accretion just near the black hole. The black hole is not emitting any radiation itself. And then, so we can't see those. They're very, very tiny, about the size of our solar system. What we can resolve is the giant narrow line region of emission that's perpendicular to that torus in the AGN. So if we figure out how that is oriented with our line of sight, we can then start figuring out how the torus and the AGN itself is oriented with our line of sight. And that's really neat because then we can start looking at other observable parameters and see how they correlate with inclination, so that we can start looking at a bunch more AGN without having to do this really complicated modeling. And so the hunt then has stopped with the Hubble Space Telescope, and we're now moving on with IFU, Integral Field Unit Spectra, that give you a data cube where you're taking a picture and then a spectrum at each individual pixel in that picture. And that's going to help us answer this really big question, why aren't there outflows in all of these AGN? We kind of were expecting that there were to be, and there aren't. So what's going on? So that's it. Thanks. No, because, I mean, there are examples. Oh, okay. Haha, Dr. Dunn. Crazy guy. Question. So I think that maybe it has something to do with just how much they're eating. And so if they're not eating as much material, maybe they're not emitting as much radiation then at the same time. And so that if there's not enough radiation coming out to push out all that material, it's just not going to turn that cone feature on yet, maybe. Or maybe what's happening for that rotation example is that the cone is just so big that it's just flat, and it's just lighting up the whole, the disk surrounding it. Maybe the disk is really thin, the stuff that we're seeing the emission from, and so that's just lighting up the whole disk then. So maybe it's just an opening angle so wide, maybe. Or it's just not strong enough to have this conical formation. So we don't know because it's really tough to do this for anything greater than a redshift of 0.035, right? So anything farther away than that, the objects are really small and you can't look at the individual kinematic components other than the nucleus, so we can't model them. So we have to only look at the nearby targets and then deduce what we can from those and hopefully apply. That's what the inclination versus infrared color is useful for them, because then we can start looking at things that we won't be able to resolve at higher redshift. Yeah, we have I mean, No, we haven't looked at, there wasn't anything, right. Yeah, there's nothing too neat from that. Yeah, I think we had there's a couple of plots that we looked at, redshift versus these things, like how many we were able to detect at a certain redshift, and there wasn't any limiting factor yet. Yeah. So the accretion disk not have a narrow line. Sure. So the accretion disk isn't doing the funneling. It's the torus, the colder dust around the accretion disk that's collimating or funneling that light into that conical structure. But yeah, I mean, maybe there's some warps that are going on that's blocking some of that emission. It's not quite clear yet. So, I mean, we have these that have the bicones, those exist, and now we need to go back and look at the ones that don't necessarily have them that we saw and figure out why, yeah. I mean, do they exist and we just haven't found them, or if they don't exist, let's start looking at the parameters between the ones that have cones and the ones that don't have cones and see what kind of differences there are. So the narrow line region is it's that emission that we're seeing the region where we're seeing that emission from. So if we, hold on one second. Right, so if we just look at this oxygen-3 image, I mean, you have the spectrum where you have these narrow lines. So these narrow oxygen-3 lines are typically only going to show up in a gas that is very sparse, but also very fried, very ionized. And so you're going to see that most prevalently just on top of these AGN, because that's where it's blowing out all this material. And so, yeah, like the inner region has this big thick torus that's not letting any emission out. You're not seeing any of this emission. And so it's just this narrow signature that we've deemed so cleverly the narrow line region.